Welcome, this is Professor Ridge. Today's lesson 7.3, Systems of Nonlinear Equations and Inequalities. Two variables. And our first learning objective, solve a system of nonlinear equations using substitution. A system of nonlinear equations is a system of two or more equations in two or more variables containing at least one equation that is not linear. So recall that a linear equation can take the form of ax plus by plus c equals 0. So if you remember too, the main characteristic really that we look at is that x is to the first power, y is to the first power. That's what's going to create a linear equation. Any equation that cannot be written in this form is nonlinear. So the substitution method we use for linear systems is the same method we will use for nonlinear systems. So we're going to use the same technique, but when we solve one equation for one variable and then substitute the result into the second equation to solve for another variable, so on, there is, however, a variation in the possible outcomes. So instead, if we had two lines, so if we think about our graphing method, right, if we had two lines, you can get one solution only if they're intersecting lines, and then of course if they're parallel lines you'd have no solution, and if they're the same line you'd have an infinite number of solutions, i.e. all the points on the line that, the two lines are the same. Okay, so now if we have, let's say we're going to start with a parabola. I'll show the picture the book has in a second, but a parabola, and let's say we had another line, you can get two solutions, or depending on how the equations, how the graphs match up, maybe you only get one solution. So what if you had a parabola that's like this, and then maybe you just hit what we call a tangent line, where it just hits in that one spot, and then also of course they can just not intersect at all, and you have no solution. So just depending on what's going on, right? So if you have nonlinear equations, you can get more than one equation, more than one solution, depending on how the graphs match up. Okay, so here's the book's picture's a little nicer than the ones I did. So you can see if you have this one parabola and then the line, they don't intersect at all, so that have no solution. And then if we just hit in one spot, you'd have one solution. And then of course it can hit in two spots and have two solutions. Okay, so let's try the substitution method. So here's the technique. Solve the linear equation for one of the variables. That's your first step. Now, technically you could solve either equation for one in either variable. It doesn't matter which. It's typically easier to solve the linear equation for one of the variables, but like in this problem, I probably would just look at the second equation, y is equal to x squared plus 1, and I would substitute the x squared plus 1 in for y. But the books, they're kind of saying, hey, let's use this method. And it's usually easier, but like in this case, I probably would do it a little different. Anyway. Step 2, substitute the expression obtained in step 1 into the parabola equation. And then 3, solve for the remaining variable. Check your solutions in both equations. Okay, so let's look at, our step 1, we're going to solve for one of these variables. Doesn't matter which. Let's solve for x, so just add y. So if we add y to both sides, add y. So we get y minus 1. And then we're going to take x equals y minus 1 and then substitute it into the other equation. So we get y equals x squared plus 1. And we're going to take the x out and put in the y minus 1 in for x. That's the substitution step. Okay, then we're going to solve this resulting equation. So you're going to FOIL this out or use the square formula. Hopefully you know that by now. So it's going to be y squared minus 2y. If you FOIL it, right, you're going to get minus y twice, so you get minus 2y. And then minus 1 times minus 1 is positive 1. And then we have the plus 1. And now this is a quadratic equation, so we're going to solve this resulting equation, solve for the remaining variable. So that's our step 3 there. So to solve a quadratic equation, we want to get it equal to 0. So we're going to subtract y. So we get y squared minus 3y, and then 1 plus 1 is 2. Okay, we got it. Now we have to factor it. So remember, this is a quadratic equation, so we got to factor it equal to 0. So factors of 2 that add to 3, 2 and 1. To get negative 3, they both have to be negative. And then now you're going to set each factor equal to 0 using the zero product property that says, hey, if you have something factored equal to 0, the only way this could be true if one of these two factors are equal to 0. So you set each one equal to 0 and solve it. So you add 2, add 1. So remember, when we're looking at the graph, it's going to be this situation where you're going to have two ordered pairs, right? The line's going to intersect twice, so they're giving you two different y values for that line and parabola where they intersect. So now what we're going to solve for the remaining variable, we're going to take this y equals 2 and plug it back into our equation 1 to figure out what x is. So let's see, x equals y minus 1. So if y equals 2, x equals 2 minus 1, which is 1. So that gives us the point 1, 2. And then if y equals 1, x equals 1 minus 1, which is 0. So that will give us 0, 1. And then that's our solution set, is these two ordered pairs. And then if we type this in Desmos, we could see that the line and the parabola will intersect at these 2 points. Or if you want to check it, you just plug it in and make sure it works for both equations. So if we do 1 minus 2, that's negative 1, that works. And then y is 2, 1 squared plus 1 is 2. So that one works in both. And then if we do 0, 1, 0 minus 1 is negative 1. 1 equals 0 squared plus 1, that's true. Okay, so you can check it algebraically, just plug it in, make sure it works for both equations. Or, let's type it in Desmos. Okay, so we put in both equations and you can see that they intersect at the 2 spots we found, 0, 1 and 1, 2. So we get the same solutions. Alright, so now intersection of a circle and a line. So there's also 3 possible outcomes depending on how the graphs line up. So if we have a circle and a line, they cannot intersect at all, so you would get no solution. You can have a tangent, and it just hits in one single point, so that would be one solution. Or the line can intersect the circle in 2 spots. So again, there's 3 possibilities. If you have a circle and a line, you can get 0, 1, or 2 solutions. Alright, so let's try an example. Find the intersection of the given circle and the given line by substitution. So just like we did before, we're going to solve the linear equation for one of the variables. So equation 2 is the linear equation. So I'm going to solve this one for y. Well, it already is solved for y, so I don't have any work to do. Right, so that's done. Then I'm going to substitute it in the expression obtained in step 1 into the equation for the circle. So now I'm going to take this 3x minus 5 and substitute it for y into the second equation. The equation for the circle, sorry. So 3x minus 5 squared equals 5. Now we're going to solve this equation. So we get x squared plus, and remember the square formula. I'm going to write it again. I mentioned it last time, but you square the first term. When you FOIL this, you get AB twice. So 2AB and then B squared. So our A is the 3x. B is -5. So normally I wouldn't write this down. Just, you know this formula, and you should know this formula because you do it. You should be doing it a lot by now. So 3x times 3x is 9x squared. And then I multiply the numbers, 15, then double it, so that's 30, and then the variable x, and then 25, so the 5 squared. And then this is a quadratic equation, combine like terms. So we get 10x squared minus 30x. Subtract this 5 from both sides. So it's 20 equals 0. Notice they all have a factor of 10, so I can factor out the 10. And I want factors of 2 that add to 3. So it'll be x minus 2, x minus 1. Okay, 10, there's no variable here, so 10 can never equal 0. So basically you just throw that one away, right? 10 equals 0, that can't happen. X minus 2 equals 0, or x minus 1 equals 0. So x equals 2, or x equals 1. Now we're going to do like we did before, and we're going to, so basically we're going to get two points, two ordered pairs, so it's going to be the circle with a line. And so we just figured out like this one will have a 1, and this one will have a 2. For the x, now you got to figure out the y for both these points. So we're going to go back to equation 2 and plug in x equals 1. So y equals 3 times 1 minus 5, which equals -2. So that gets us 1, -2. Or when x equals 2, I switch the order, it doesn't matter. When x equals 2, oh, my drawing's off. This would have been the 1. This would have been the 2. And then, so we put in the 2 into this equation. So y equals 3 times 2 minus 5. So y equals 6 minus 5, which is 1. So it'll be 2, 1. Okay, and then again we can check it algebraically. 2 squared plus 1 squared is 5. That's true. 2, no, this would be 1. 6 minus 5 is 2. Wait, 6 minus 5 is 1. So it'll be 2 for x and 1 for y. So that one works. And then if I plug in the 1, -2, 1 squared plus -2 squared is 1 plus 4, which is 5. And then if I put in the 1 for the x, so if I check it algebraically, if I put in the 1 for the x and the -2, so you get 3 minus 5 is -2. Right, so you check each point, you got to check in both equations, so you got to do 4 checks. Or now you can't do this again on the test because you want to have a graphing calculator available, but for homework you can type it into Desmos and check it that way. In fact, I would like you to do that. I want you to get used to looking at the graphs. Okay, so you can see the circle with radius square root of 5, which is about 2.23. So we got the circle centered at 0, 0. And then the line y equals 3x minus 5, so it crosses at -5. The slope's up 3 over 1. So you can graph these by hand, by the way. And then you see we get the same points that we just found algebraically. 2, 1, and 1, negative 2. I believe that's what we had. 2, 1, and 1, negative 2. 2, 1, 1, negative 2. Okay, so our solution set is the 2 points, the 2 ordered pairs. Okay, so now we're going to solve a system of nonlinear equations using elimination. And our first example that we're going to look at using elimination is we're going to solve a system that has a circle and an ellipse. So it's always good to kind of think about what are the possible outcomes. So again, depending on how the circle and ellipse interact with each other on the graphs, you can get no solution. You can get 1 single point as a solution. You can get 2 points. You can get 3 points or 4. So you can get anywhere from 0 to 4 points depending again on how they interact with each other. Okay, so example 3, solve the system of nonlinear equations. So the first equation is a circle, the second equation is our ellipse. And what we're going to do is just like with the linear equations using elimination, you want to eliminate one of these variables. So I'm going to eliminate the x, and I can take equation 1 and multiply it by negative 3. Okay, so negative 3 times 1 would be negative 3x squared. Negative 3y squared equals negative 78. Equation 2, we're going to leave it alone because, see, I wanted to get the x squares to cancel. So we do pretty much the same technique. The x squares cancel. We get 22y squared equals 22. Now we're going to solve this, and there's a couple ways we could do it. Since there's no middle term, no y, it's just y squared, we can just get the y squared by itself and then use the square root property. So we square root both sides and we get plus or minus square root of 1. Okay, so that gives us 2 answers. So y equals 1 or negative 1. Now we're going to plug it back into equation 1, and we put in x squared plus, now notice it doesn't matter if I use 1 or negative 1. From here it'll be the same thing. So if y equals 1, you're going to get 1 squared equals 26. So x squared plus 1 equals 26. Subtract the 1, 25, and then square root it, plus or minus square root of 5. So if y equals 1, x could be, square root of 25, which is plus or minus 5. Okay, so that's going to give us 2 answers for y equals 1. So we get positive 5, y is 1. We get negative 5, and y is 1. And then if y equals negative 1, you're going to get x squared plus negative 1 squared equals 26, and then this is going to give us the same result. Okay, so I'm not going to show all the work. I'm just going to jump to x is plus or minus 5. So we get 5, negative 1, and 5, or negative 5, negative 1. So our solution set's going to have 4 points. We get 5, 1, negative 5, 1, 5, negative 1, and negative 5, negative 1. So it's that last case where it's going to be something similar to this, where you're going to get 4 points. So let's look in decimals and just verify. Or again, you can plug in all the points, but again, I'm just going to use decimals. Okay, so there we go. So you can see we have the 5, -5, -1. Oh no, -5, +1, -5, -1, 5, 1, and 5, -1. Okay, so we get all those 4 solutions. So it's an ellipse and a circle, both centered at 0. The ellipse has, or the what do you call it? The circle has radius square root of 26, which is 5 and a little bit. Well, they're not showing you what that is. Here you go. It's 5.09. Take square root of 26. Okay, our next learning objective, graph a nonlinear inequality. A nonlinear inequality is an inequality containing a nonlinear expression. So basically, if you have anything that's not x to the first power or y to the first power, that's going to be nonlinear, right? That's typically what makes linear. X is to the first power, y is the first power, right? That's what makes it linear. So anything that's different from that would be nonlinear. And graphing a nonlinear inequality is much like graphing a linear inequality. So if you, let's look at these parabolas. So if you did y is greater than, that's the inequality, x squared minus 4. So if you recall when we did the lines, if I wanted to do, say something like y is greater than x plus 2, you would go to the line y equals, let's see, the y-intercept's 2, slopes 1 over 1, and you put a dotted line. And then a couple different techniques. You can do a test point to see which side of the line you would shade, or you could do, if the shortcut, if you solve it for y, you can put your pin on the line and y is going up and down. So if y is greater than, that's going above the line. That's kind of the way I think of it, and you shade it. So same thing here. So instead of it being a line, we have this parabola, this curve. And if you have it solved for y, you can just put your pin anywhere on the curve. Y is greater is going up. So that's how I know where to shade. So you can do it that way. That only works if it's solved for y, meaning y is all by itself and then greater than or less than whatever the expression. If you have the equal to in it, it's a solid line. Greater than's going up. If it's less than without the equal to, it would be a dotted line, or a curve, I should say, a dotted parabola, or dashed. And then y is less than, well, put your pin on the curve, and less than is going down. So that's how I know to shade below that curve. And then the equal to would just be a solid line. Okay, so that's kind of, so whatever the inequality is, you graph the inequality and then you shade the portion of the graph that makes the statement a true statement. So again, another technique could be I can pick a test point like 0, 0 and see that 0 is greater than 0 minus 4. That's true. So this is in the shaded region, so I shade that region. So that's the other technique. So if you have something like a circle where it's not solved for y or x, then you would do the test point method. Okay, so let's try graphing the inequality for a parabola. Graph the inequality y is greater than x squared plus 1. So first we're going to start with the curve, the y equals x squared plus 1. So again, you should know your toolkit function, this one. So x, y, 0 squared 0, 1 squared 1, 2 squared 4, 3 squared 9, and then we're going to shift it up 1. So we're going to start at 0, 1. Now for this, if you don't want to use the transformations, you could just do the plus 1 and then add the 1 to all these points. That's fine. It's simple enough. So 0, 1. So again, I'm using my transformations. I shifted it up 1 degree. So my pretend origin is at 0, 1 instead of at 0, 0. So I'm counting from here. Oops. Let me try that again. So I'm counting from my pretend origin, 0, 0, my basic toolkit function for a parabola, x squared, 0, 0, 1, 1. Again, I'm counting from my pretend origin, 2, 4, 3, 9, which is probably right about there. It'd be at 10 on the real graph. And there's no equal to, so we're going to make it a dotted line. And it's a parabola, so try to make that parabola shape. Now, okay, so graph parabola f is an equation that's the boundary, right? So that's the boundary line. So it separates the graph into two pieces. So I think of it as inside. So think of it as, see, I'm going to do this. Think of it as inside. And then think of it as, let's use this orange one. Think of it as outside. See, those are the two regions. Okay? So what we want to do is figure out which one of those to shade is the true graph. So we can do the shortcut since it's solved for y. We got y is greater than. So we would put our pin on the curve and y values are above, so it's going to be this blue region. Okay? Let me erase all that. Okay, so if we do the shortcut, which is not here, they want you to do a test point. Test a point in one of the regions to determine whether it satisfies the inequality statement. So if you pick 0, 0 on the real graph, not the pretend graph, and plug it in, is 0, 0. We're going to test 0, 0. So is 0 question mark greater than 0 squared plus 1? Is 0 greater than 1? And the answer is no. False. So if this is false, the region that's outside, the other region would be true, and that's what you would shade. Oh, I don't have my highlighter. Okay, so we'll just shade. Okay, so you're going to shade it like that. So let me show you on Desmos. You can type in the greater than or less than symbol, and it'll show you the shaded region. Okay, so it's pretty much exactly what we drew. So 0, 0, or 0, 1 if you move it up 1, and then counting from here 1, 1, and counting from here 2, 4, which is at 5. So on, and you make your dotted line, and then you shade above, or you can think of it as the inside region. That's the other way I think of it. Okay, so that region is what makes it true. So again, the solution set are all the points that are in the shaded region. So it's not the curve. In fact, the curve would be false. It's all the points that are within that boundary line. So everything that's shaded is a solution. And there's an infinite number of points in this shaded region. And our last learning objective for this section, graph a system of nonlinear inequalities. Okay, so graphing a system of nonlinear inequalities. So basically a system of nonlinear inequalities is a system of two or more inequalities in two or more variables containing at least one inequality that's not linear. Okay, graphing a system of nonlinear inequalities is similar to graphing a system of linear inequalities. The difference is that our graph may result in more shaded regions that represent a solution than we find in a system of linear inequalities. Okay, so you can have more regions too, depending on how things intersect. So the solution to a nonlinear system of inequalities is the region of the graph where the shaded regions of the graph of each inequality overlap. Okay, so this where the regions intersect. Okay, and we call this the feasible region. So for instance, if we had, let's say we had something like, well, like a Venn diagram, right? If you had two circles and you wanted to be inside both circles, the region that overlaps for that would be the solution if you're inside both circles at the same time. If you wanted to be outside both circles, then it'd be the region like that. So just depends on what the inequalities are and so on. Okay, let me erase that. All right, so the technique then is you're going to graph both nonlinear systems. Here they say find the intersection points by solving the corresponding system of nonlinear equations. You don't necessarily have to do that. Depends on what you're going to do. So sometimes it's helpful to know those vertices. If you graph it really well, sometimes you can see what those are, so you don't have to figure that out algebraically. Graph the equations. Find the shaded region of each inequality. Identify the feasible region as the intersection of the shaded regions in each inequality, or the set of points common to each inequality. So we want to look for the intersection of basically the overlap. Okay, so graphing a system of inequalities. So graph the given systems. So the first equation, or both of these equations, are actually parabolas because we have just x squared and y is not squared. So let's see, I'm going to solve both of them for y. So for the first equation, I'm going to subtract x squared. Actually, what I would have done is just move the y over and then flip the whole equation. But you'll see it gives you the same result. Now, when you divide both sides by -1, you got to flip the inequality. So you get y is greater than or equal to x squared. Well, that's our basic toolkit function. 0, 0, 1, 1, 2, 4, 3, 9. So mirror image. And then we want to do a parabola. And then if we went 4, it'd be 16. So it's going up like that. Okay, and the same thing here. Oops. Okay, and then I have it solved for y. So what I do, okay, I'm not going to do it the way the book just mentioned. So I'm just going to put a couple small arrows from the line going up. So I'm thinking I kind of think of it as inside that parabola. So I just do a couple just to remind me. So 1 is basically inside this parabola. So now let's do the inequality for 2. I want to get y by itself, so just subtract 2x squared. And then this is, let's see, it's our basic parabola. 0, 0, 1, 1, 2, 4, 3, 9. But then we're going to multiply by -2. So the negative is going to flip it upside down. And then the 2 is going to make it skinnier. And then this is moving it up 12. So I'm going to start at 12. And then that's going to be my pretend origin, 0, 0. Okay, so I'm not going to draw the pretend axis, but 0, 0, 1, -1, times 2. So 1, 1 times 2 would be 1, -2 from the pretend origin. So 1, -2. And then this will be 2, -8. So 2, 1, 2, 3, 4, 5, 6, 7, 8. See, that's where they intersect. And we got the mirror image on the other side. And then this one would be 3, negative 18. So 3, let's see, there's 12, 13, 14, 15, 16, 17, 18. And then we make my parabola. Not very good on that one, but hopefully you got the idea. And then since I have it solved, I want y is less than. So again, I go anywhere in my curve. Let's do blue for this one. And going down. So that's on the inside. So basically I want the region that's inside both of these parabolas at the same time. So you could see that, hopefully you could see that the solution set is going, I wish I had the highlighter. There, we'll make it this color. So the solution set's going to be all of this. Yeah, I wish I had the highlighter because it looks a lot better when it's shaded with the highlighter. But anyway, so whatever you want to call this color, it's that region, that colored region. Ooh. I think I overloaded my computer there. Okay, so that's our solution set, is this, whatever color you want to call this, kind of reddish fuchsia or whatever it is. I don't know. Okay, so basically it's inside both of those parabolas, right? And that's the solution set. Okay, here's the picture from the book, a little nicer than mine. But again, just to emphasize, the solution set is everything that's shared by both of them. So it's this region here that's inside both at the same time. So basically in here, through there. Okay, so the overlap. Okay, so that brings us to the end of that section. So again, practice, practice, practice. Go to the end of the section, do the section exercises, all the odds. If you can, do a few more, and I will see you next time.